his eyesight was good enough, he could do that and say, you know, in the spotlight and say, oh, he sat in the back of the boat.
My eyesight might be good enough, but I'm not gonna look at them long enough. I want to do it.
Oh, see, we were selling them, this was in the early seventies, we were selling pitch since we put the, all the university.
Oh, really? Yeah.
That's good money back then, or it was to us. 15, 16. Seemed like
And
that.
open yourself to work a lot more.
Huh?
Open yourself to work a lot more.
Somewhere I don't think I love coming.
That ground goes high dollar.
Yeah, maybe it does. You ever go down to the secretary with mine, where they milk? Dr. Hoss down there. I've seen the thing. He milked some cobras too. He got bit by 3 times.
Seen that too.
I went down there one time. Watched several times.
It's crazy. Australian crocodile wins the
What is supposed to
Steve Irwin. Went around the creek. I asked him
That's what it's
going
about.
around pulling the tails on things, and should have been finally went over and killed him.
Yeah. And he wasn't even bothered, he was just
Yeah,
swimming
that's
there.
what they say. Do you believe that?
I don't know what I believe in that.
Have you ever seen any picture of him where he was just leaving it alone?
No. Yeah,
Stingrays never bother anybody, but he gets stingrays. If you step on him, it's usually when
They got, he stepped too close to this one, they got him in the leg. They told him that was,
Well, they tell you to shuffle your feet, don't pick up your feet when you're in there. Because if you go under them, they'll just take off. You step on top of them.
this one was in the way, just walked into the water. And I think he stepped close enough to it to tackle it.
I never saw one single picture of that man when he went in the harassment.
What got me at that time?
This is the deadliest snake in the world. Let me grab it by the tail and swing it around him.
Brown.
Yeah.
And then he got down where he had the spiders that had him. Actually, see them.
Drooping off.
Not the thing. He's holding the roof, you know, and he's walking around.
It's not enough to take the picture. You gotta harass it a little bit. Yeah, he almost got his wife killed on that. See that? He took her rock climbing, and she wasn't experienced enough. She got hurt off there. He almost- Pictures of him feeding those crocodiles with a baby, and it just wasn't all wet. He had a few screws.
Same way. I got 2 screws loose too, so I'm missing. Got 50 more to go.
Yeah, I got more notes back here. I got notes like crazy.
Can you tell me whether or not I've got that functional function by looking at my stuff, right? Oh, unless you're busy.
Yeah, after I get this demo set up.
Okay. The book I got on that thing is about 3 pages long, it ain't worth a while.
Let's get a good right.
You got a lot more reading on Moodle than you had on the board.
Yeah.
Is that, as far as this book is concerned?
Just follow the assignments that I give you.
Okay.
Gee, the reason people don't do demos is because they take a lot of time to set up.
What's that?
The reason
Oh,
teachers
yeah,
don't
they
do
do.
demonstrations is because it takes so long to set up. Okay.
Unless you keep all the materials you need for it to set up, and, I mean, not set up, but gathered up into a box or something.
Yeah, I've already got boxes.
Huh?
Yeah, I've already got them in boxes.
But it still won't work.
Too much play in it. It's loose. Oh, there we go. Oh.
sulfuric acid is a bit too like vinegar, white vinegar, what's it still like that? It is mild acid.
Yeah, a lot of different acids work. I have it. I don't know if I've tried it or not.
I was just wondering if it give a more consistent voltage or current
Yeah.
than in the salt water.
Yeah, I mean, you can try a lot of things. Feel free to try it at home and let us know.
I don't have zinc plated rod.
Well, just anything, almost everything's been played with zinc these days.
Oh yeah.
Yeah.
Okay. Oh, just a zinc plated bolt would work.
Yeah.
I got plenty of them.
Yeah.
A few thousand of them. A few hundred of them.
Yeah.
I think I 16D nail hot dip would probably work really good with.
Yeah,
Just got a
these
lot
are
of
kind of
them.
oxidized, but you gotta find a nice shiny nail or something.
See, this one was electroplated. If you get a hot dip one, it's got a lot more zinc on it. This is electroplated.
Oh, really? Yeah,
The hot
something
dip
like that.
galvanized. Yeah, that's electroplated. If you get one that's hot dip, it's got little lumps of zinc on it.
Mm.
Because they just dip it in the hot, that's all they do.
Oh, yeah.
So you don't see a lot of bolts hot dip, but nails are a lot of them are hot dip. I'll bring you some. I got about 3 50-pound boxes of 16D nails. I'll bring you some.
Yeah, mine's all,
I might have to dig them out.
mine's all nasty. Those are pretty old. Well, I guess we're about ready to get started. Oh, you know what? I need to test something. Get started. Okay, we're going to get started now. I'm just going to call your name and...
This buffer, we're going to actually use this.
Yes.
We are.
I'm going to go ahead and get started. This is DC circuit analysis. And when I call your name, you should have a reading assignment, so I want to check your reading assignment to make sure that you've taken notes. Corey?
I haven't last time.
Did you take some notes on the magnetic, the batteries, or the electromagnetic? Oh, okay, haven't taken notes. Okay. Okay, that book is free. Just let everyone know it's a free online book on Moodle. Benjamin?
Free online.
This book. The first book we're using is just a free ebook. But that's just for the first week. And then after that we're using the bookstore book. The book that we've been reading out of so far is free online ebook. Okay. So, Benjamin.
That was the other book that I didn't have.
Yeah. Dakota's not here. Jesse, do you have anything to show me, Jesse?
It's on the move. He's got shows on.
Yeah, let's get some synchronization. Is that it? Mesh loops.
Let's see. What have you been reading this stuff from? Total resistance circuit. Did you read anything about the batteries or anything like that? About the effects of current?
Oh, all those current drawings and stuff.
This book.
Oh,
You read this book?
That. I don't have that.
It's free online. It's an ebook, free online. And I got copies that I gave out, paper copies.
Really?
Yeah. It's a.
He has
Have you ever
that
been to
one.
Moodle before? Have you
Yeah.
been to the Moodle site?
Yeah.
Okay,
I
it's
go
on.
to it all the time.
It's on there. It's on Moodle.
Okay.
Okay, you can.
On this class. On 138.
Guys, we don't have this much time to talk about this much stuff, so this is all set down. I call your name. If you have it, then that's great. But get with someone who has been doing it and try to figure this stuff out. We only have like 70 minutes in class. We don't have time to do this every day.
Yeah, that's how come I didn't understand how it's supposed to do all the circuit drawings and stuff and read those.
Christopher Drew. Okay. Okay. Thanks. Good job. Get with Christopher because it seems like he knows what's going on. If you don't know what's going on in the class, talk to Christopher because he's got all this stuff together. Frederick. Okay. Okay, good stuff. Okay, good. Robert Lambert.
This is what I've done on the first reading assignment.
Okay. Metal attraction, electrolysis. Okay, you need more in there. That's a good start, but you need more in there. Okay. Okay. Gary Nichols? No notes. Don?
I don't have one.
You don't have notes. Okay. Clarence?
Basically 9 pages.
Okay. Good. You guys can talk to Clarence too and see what he's doing. He's taking some really good notes. Okay. Benjamin. Who's Benjamin? Which one? You're Benjamin. Okay. Just make sure you raise your hand and make sure I know exactly who you are, because I would thought you just had a question. I didn't know you were. Okay. Were you absent on
Yes.
Wednesday? Okay, you were.
Wednesday, Thursday, and Friday last week.
Oh, that's why I don't know you. Okay. Okay. Yeah, okay. I thought maybe you dropped or something. Okay. I'm going to do some demos if you guys want to come up here and see them. today we're going to talk about magnetism, electromagnetism, Faraday's law, and things like that. I did have this little motor thing working, but then it just stopped working, so I'm probably not going to be able to demo that, but I can show you the basic principles of how it works. Okay, so magnetism. This is a natural magnet. I got that from some little place, but anyway, it's I think I got it from one of those mountain towns or whatever. I don't know if you guys have seen that before. I don't really know what it is. So this is a magnet. It has a north and a south pole. You guys can see how it affects the compass. The compass is basically it's a magnet as well, so that's why it's attracted to this magnet. You also have magnetic material that's not necessarily magnetized. Okay, this is not necessarily magnetized. It may be a little bit because it's steel. The way it works out is that harder things, softer things are easier to magnetize. But softer elements, softer metals, they're easier to magnetize, but once you remove the magnet, then the magnetism goes away. So that's why iron is good for magnetic materials like electromagnets, because the magnetic domains inside of the metal, or the atoms, basically, it's softer. They tend to be softer, typically. Is you induce a magnetism into them, just the same way that if I take a plastic tube and I rub it with cat's fur or something, I can induce a voltage in a metal little ball suspended like it did before. Okay, we force or we induce an attraction. And so this is called magnetic induction. You can induce, for example, I can induce this paperclip to become magnetic because this side of the paperclip will now pick up this paperclip. So I've magnetized this paperclip. And because it's steel, it's harder, then I can actually permanently magnetize this. Now iron would be almost impossible to permanently magnetize because it's softer, and so the magnetic domains are more easily moved. It's also easy to demagnetize something by striking it really hard or heating it up, and that makes the magnetic domains inside of the atoms realign randomly. So inside of this paperclip, the magnetic or the atoms are randomly oriented, so there's no tendency for it to become magnetized. Whereas this would have all the magnetic or the atoms spinning around the same direction. And the spinning electricity, the spinning electrons creates a magnetic field inside. We'll talk a little bit about that later. But so you can see that this picks up a lot of paper clips, right? So it has the force or the ability to pick up, we call that magnetic strength. Now, when I take a piece of steel, or I think it's a piece of steel, and then I put this magnet on it, see, what it's doing inside here is it's reorienting the magnetic domains inside here, and it's inducing magnetism on this, making it magnetic itself. Okay, so it's inducing it. It's changing those domains, and it's using that energy internally. Now you can see that this does not pick up as many paper clips as it did before. Before it picked up all of them, right? Easily picked up all of them. So what we say is that some of the magnetic energy has been expended inside of the metal. Okay. If I had a bigger piece of metal, it would expend all of them, and I wouldn't be able to pick up any paper clips. Okay. So that's how you can use metal as a magnetic shield. Radio waves are electromagnetic radiation, which means that they have both magnetic and electric properties. Whereas this only has magnetic properties. And we say that separation of charge and magnetism together are electromagnetic. And that's how radio waves travel. Okay.
So tin roofs would be good for that. You want the radio on?
Yeah, I wouldn't be good. Okay, so that's good. Now, what we can do is we can this. We showed last week how that. Okay, what is this? This is a coil of wire with a nail in the middle of it. Oh, let's try this one first. Okay, can't really pick up anything first. Let's put this in here. I actually have two coils of wire. Okay, electromagnet. Everyone's seen electromagnet before, right? Okay. So that's pretty cool. Also, we can take this electromagnet and we can operate it in reverse. Okay. Can you guys see this movie? I don't know if everyone can or not. If I need to get a bigger magnet. Can you guys see that?
Mm-hmm.
Everyone see it? Causing the voltmeter to move. So what I'm doing is I'm taking this magnet, I'm moving it back and forth across this. So I'm basically generating a voltage here. Okay, that's the generator principle, the principle of how a generator works. The idea is that really what one way to think about this is this steel is made up of atoms, okay? And atoms are randomly oriented. When I put this magnet up here, it causes those atoms to align with the magnet, okay? Which gives the atoms energy, which causes electrons to be flying and slung everywhere, okay? Which shows an electrical property. That's the easiest way to think about it, okay? And we're swinging them, since they're all swinging the same direction, they all tend to add up in one direction. Okay, so that's the generator principle. What else? Let's do the little amplifier experiment real quick. Oh, and I did forget to mention, it's okay. I did forget to mention that, did forget to mention that the basic fundamental principle that describes this action, or just in the generator, was Faraday's law. What it says is a changing magnetic flux across the coil of wire induces a voltage into the coil. Okay, induces a voltage. It throws those atoms asunder, I guess you could say, and brings them around and all in the same direction. So what I want to do here is take this thing. Where did this cord is coming? Where's that? Okay, there it is. It's kind of hard to see with all these wires here. What's going on? The best way to get a good feeling for Faraday's law, which we just saw with the generator principle, is here. This will allow you to hear Faraday's law, which is kind of cool. I just came up with this last night, actually. Hear Faraday's law. Is that humming? It should be humming. Okay, you may have to get really close to it. Everyone be really quiet. Listen to this. Okay?
Like a scratch sound come across.
All this is a nail with wire around it. I'm connecting this to the input to the amplifier, and I'm moving this magnet across it. That's all I'm doing. There's no voltage here or anything.
Right.
Okay? So it's actually producing a voltage. Now, tell me if you can... Oh, let me put it closer over here. So, well, one thing you do is... But if I touch it here, there's nothing. There's not a microphone here. There's nothing in here. It's just a coil of wire and a nail. But it acts like a microphone to the
Right.
magnet. To the
Right.
magnet. Acts like a microphone. Okay? What's this? If I could do it without touching it. Now watch this. Watch when I do this. You hear anything? No.
Not much.
No, you don't hear anything. Why not?
Because you're following the lines of flux and still crossing them.
It only makes a sound when you
Get to the
go
end.
in the transition of the magnet.
Right. We get to the end.
In here, it doesn't make a sound. So that's Faraday's law, hearing it. That's hearing Faraday's law. It says that a changing magnetic field induces a voltage,
Okay.
not a constant magnetic field. And what we do is we say that this is a north and a south pole. What we do is we say that it has magnetic field lines that you can't see, force field lines.
Lines of flux.
Yeah, it's a force field. There's a gravitational force field, there's an electric force field, and there's a magnetic force field. Just like in Star Wars, you got force fields. Well, they really exist. Okay, you got the gravitational field, magnetic field, and static electricity field. What else? Oh, okay, this is the last demo, I think, for today. I was going to show you my little generator thing here, but it broke. I don't know, I'll have to troubleshoot it later. If I take this nail, I combine these two principles, I'm going to put this nail, and now I'm going to magnetize the nail, right? The nail right here. Like that, maybe. Take this paper clip. I did have a paper clip. Oh, here's my paper clip. We'll try this one. Maybe my magnet's too big.
I was using it as a pickup. That's that's like a pickup.
Now put it over here.
It's out of tune.
Listen. Okay, you hear that? That's the amplitude. Okay, put it over here.
Are you touching the nail or what?
No, it's not touching it. You hear it through the amp?
Yes.
It's being amplified. So what's happening right there is you have a magnetic field. Now remember, what did I say happened to a magnet when I put it to this? It sucked up some of the magnetism,
Yes,
right?
sir.
What this is doing is when it gets across this, is it's sucking up some of the magnetism. It's changing the magnetic field inside of the nail. That's how a guitar pickup works.
Like a pickup. It's awesome.
Okay. Now what you can do is, of course, with electromagnet, is you can this is just a coil of wires, the same thing that we have right here. It magnetizes this. Of course, it's going to, if you magnetize this, then you could obviously see that you could attract it, and then it has a commutator, actually, that it'll attract, for example, north and a south. A north and a south pole are attracted, so it makes this north, makes this south, they're attracted. As it has enough inertia to get around, then it flips it and makes this one. If this is north, it makes this is south, so it keeps making this one south. That's what it does with the commutator. The commutator is basically have carbon. Carbon is conductive. It's like the pencil lead, graphite, anything that's carbon kind of based, has electrical properties. And it just continuously flips that pole to where this will be south, and you have to kind of kickstart to get it going. Unless you have more windings, then you can just kind of play some games and make it start off. So that's the motor principle. I showed you the basic generator principle, Faraday's law, and application of a guitar pickup. So now we'll just do the slides.
That's cool.
Any questions on that?
Can you turn an electric motor into a generator?
Mm-hmm. Yeah, you can. Electric motor and generator, they work
So if
in
you put
reverse.
voltage into an electric motor, it'll generate mechanical energy. If you put mechanical energy into an electric motor, it'll generate voltage.
Yeah, you can spin this shaft and it'll produce a voltage. Yep.
That's interesting.
Yeah, I just came up with that little demo last night. I want to try to get that one on YouTube or something.
Mm-hmm.
That'd be a nice one to put there. Okay. So today we're going to be talking about magnetic. Oh, sorry, the thing is muted. Magnetic effects of current. And the first thing we talked about was magnetism. Actually, in that book, in the elementary lessons book, that's an ebook that's free online, that's on Moodle, that I passed out the first day or whatever, some paper copies. It has an entire section on magnetism and all those. There's lots of properties of magnetism that you You're not going to understand a lot of things if you don't really understand the properties of magnets and how they work and how magnets are more than what you than just picking something up. There's a lot of properties to them that are not self-evident. You have to do a lot of experiments. So if you're interested in magnetism and to know the properties of magnetism to the level of being able to design things like a guitar pickup or design something, invent something new, you need to read everything you can about magnets. Okay? So the reading assignment, we've already kind of read some of these, and I don't really know. These slides were made for a class where we went more in depth, and I had you read some of these. But I think you read a little bit about galvanometer, electromagnets. Okay. These are some of the inventions through the progression of magnetism through time. We had Orsted's discovery he discovered that a current would produce a magnetic field. It was by accident that he discovered this. He had a compass next to him, and he was playing around with Volta's new battery and wire, and he noticed that the compass moved. And galvanometer, 1820. Galvanometer was the current meter, basically. I did forget to show you that, but if you take this compass and wrap a wire around it, which I did, and put a voltage across it, then it'll make the compass become parallel with that wire. And that's a basic galvanometer right there. Just take a wire and wrap it around a compass. And you can see that it can measure. And actually, it'll very easily line up, but actually if you take a magnet next to it and try to, for example, force it parallel with this wire, then it'll actually measure the strength of that current. Yeah, because the stronger the current, the more it's going to try to push this needle tangent to that wire. Okay, so you can make a simple galvanometer right there. So a lot of all the early, before we came out with the digital technology, almost all of the current meters and all of the meters that were used to develop, vacuum tubes and a lot of the things that we have today, was just simply you're measuring current indirectly. You're measuring the current by measuring the magnetic field. So really, you're measuring the magnetic field. That's why magnetism is so important to electronics. And then Faraday, in 1821, magnetic rotations, he discovered that the properties of the magnetic field were a magnetic field rotation around the wire. And then Sturgeon in 1825 designed the electromagnet, Ampere, the solenoid. Here's some videos you can watch at home. We're not going to watch them in class about magnetism. Yeah. Yeah, it'll be. So the connection between magnetism has long been suspected. Lightning had been known to magnetize knives. During this time, all attempts to magnetize objects had failed by putting currents through metal. But in 1819, Oersted of Copenhagen showed that a magnet tends to set itself at right angles to a wire carrying current. You can see here, if you have a compass oriented parallel with the wire and then you force current to flow, then the needle will tend to go tangent or perpendicular to that wire. You can see with the blue wire, that's what I'm trying to show with it's kind of light colored. And so in 1800 was when the voltaic pile was invented. That's when they started doing these experiments. So one invention led to other experimentation and other inventions, which is pretty typical. Found that the direction of the compass depended on whether the wire was above or below the compass, and then Ampere's rule was that if you suppose that it tells you the direction of that magnetic field. He said that suppose a man swimming in the wire with the current and he turns to face the needle, then the north seeking pole of that needle will be deflected towards his left hand. So it shows that, imagine yourself, kind of being the electron. He's saying that it's going to cause you to deflect or turn in the current. The deflection of the north pole of the magnetic needle as viewed from the conductor is towards the left. So really what he's trying to say is that there's going to be a force on you on the on the wire or on the compass itself. Remember, forces always come in pairs. There's going to be a force on the wire, there's going to be a force on the compass. But because he's holding the wire, of course, nothing will happen to the wire because he's holding it. And like I just showed before, just with this compass with a wire around it, that's exactly what's on the screen here. You have a compass and you're putting a wire around it. So that's all that is, and it shows that thing will be deflected. And that was the first galvanometer. And this on the screen is the same principle as this as well. It's a very easy experiment to do. Okay. Now we'll get into magnetic rotations. Now this is, you can demonstrate this with a projector if you have a wire and you have some iron filings, then you can actually show that the magnetic rotations around the wire are in the direction as shown. And usually we use the right hand rule to show the rotations of the magnetic field. And the way that works is, if you say your thumb is the current in the wire, then if you wrap your fingers around the wire, that's going to be the direction of the magnetic field. And the direction of the magnetic field is always defined as the north pole. So if I have an arrow pointing, my fingers are pointing, counterclockwise?
Right.
That's going to be the north direction of that pole. So that's just the way it was defined. So it's kind of a complicated magnetic field because it's not really a magnetic field we can produce in the real world with a real magnet, because normally we just have straight line magnetic fields. Of course they twist around, but these magnetic fields around wires have a very strange shape, I guess you could say. So if you look at this, imagine that a wire was going into this page on the screen, then the magnetic field around the wire would be in the direction indicated. In other words, if you were to put a compass next to this wire, all these needles would be pointing in the direction indicated. 1, 2. So if you had 5 compasses, or I guess that's how you say it, compasses, then around this wire, then they would all be pointing as indicated on the screen. Okay, which is very odd to me. But so we say that it has a magnetic rotation around the wire. Now, if the that's going in to the page, and you can use the right-hand rule to look at that, the right-hand rule, wrap your finger. And then if the current is coming out of the page, you can use the right-hand rule again to show the correct direction.
Right.
Does everyone know how to do that? It's clear on that? All the questions? So you can see actually what happens on the inside of the wire. If this wire is a category 5 wire, and it's going down, and we've magnified it, and we see that this is the insulating material in between, and there's a slight air gap in between the wire, then it shows that there's going to be a magnetic field inside of it, and these are going to add together, right? They're going to be both going in the same direction. Agree?
Right.
Okay. Actually, it's kind of deceiving, though, because this is only showing the magnetic field at one point, this distance from the wire. Actually, if you measure out here, you can detect the magnetic field out here as well, but it's weaker. Okay? So the magnetic field is really strong right here, strong, weaker, 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 and it gets weaker as you go out. Actually, the magnetic field, there is a magnetic field on this side of this wire from that wire. Okay? Because it doesn't matter that this wire is here, the magnetic field is still going to go out this way. Whether or not you have a wire here or not, you're still going to have a magnetic field out here from this wire.
Right.
Right?
Yes.
But the thing is the magnetic field of this wire over here is in this direction, whereas this one is in that direction. So those tend to cancel each other out.
Okay.
But these in the middle tend to add to each other. And since it takes time to build up a magnetic field and it takes time to dissipate a magnetic field, there's a time delay. And what happens when the magnetic field changes? Let's say you're sending digital data down this transmission line, and the current is going up and down. What does Faraday's law say when the magnetic field inside here is changing? It induces a voltage, right? You think we want that? Just random induced voltage? No. Causes noise in the wire. So twisted pair wires, what do they try to do? Suck them as close together as possible. That's why you twist wires together.
Right.
Twisting them together increases the bandwidth greatly. If you put some iron filings around a piece of paper, put a wire through it, then you'll get this pattern that you see, which again proves that there are magnetic rotations around wires. Put the iron filings in there, tap the paper, and then you'll get that. So, what we say is that the magnetic field in a wire is proportional to the current through the wire. We have this constant called the permeability. Permeability is the tendency of the media around the magnetic material to promote the presence of the magnetic field. Okay, it's called permeability. So we use this constant. So there's a permeability for air, and there's a permeability for iron. There's a permeability for different things. So different substances have a different ease of the magnetic field to be generated. For example, a magnetic field is going to like to have a nail or iron better than it's going to like to have air in the middle. Okay, so you can make a better inductor, a better electromagnet with magnetic material inside of it, something like iron that has a higher permeability. And this is the number we use. We use this Greek character mu to represent the permeability. This is more of the right-hand rule, which I think hopefully you guys... And this is showing the two wires going into the page, or going coming at you. This is like an arrow. The arrow is going to come to you. And then the next one is like you're seeing the tail pins of an arrow, so it's leaving the page. And you can see that in actuality, the two fields overlap each other. And the ones in the middle add, and the ones on the outside tend to cancel. That's what I'm trying to show there. I kind of drew that on my own, just trying to describe that. So what you get, kind of, is the total net effect is mostly you get this magnetic field in between the wires only. And it tends to be like a north-south pull of a magnet. And that's why you have this electromagnet. That's why this is electromagnet. Because you have a wire coming this way and then that way. So you have the wires wrapped around opposite directions. Okay, the current's coming this way and then it's going that way. If the currents went the same way, then obviously they would cancel. We have some videos you can watch at home to learn a little bit more about it. Here's more of the same thing. B, the magnetic field inside of the wire loop is proportional to the number of wires in number of loops. So I have a lot of loops around here that I made. The reason I made so many loops is not because I really wanted to spend a whole lot of time making loops last night, but it's because I wanted to increase the magnetic field. So that's what this equation is telling you, that it's going to be proportional to the number of loops that you have, directly proportional. Also proportional to the magnetic material. If I would have used air, then I would have had a permeability of mu naught. But if I use iron or something that likes magnetic fields better, then I'm going to get an amplified version of my magnetic field inside of it. And then, of course, I is the current that you put through the wire. Of course, if you have too much wire and if you put too much current through it, it's going to heat up as well because it's going to be like a little heater. I think everyone's pretty familiar with electromagnets, but this kind of shows a basic diagram of the concepts we've learned so far with a zinc and a copper through a wire. It's kind of neat to show that really with just water with salt in it, a zinc-plated nail, and a piece of copper, and a loop of wire, you can produce a lot of things. You can produce a current, a voltage, and a magnetic field. with just that. Maxwell's rule says that every portion of the circuit is acted upon by a force. This is showing that we're inserting something into this coil, this wire coil. It says in this situation, every portion of the circuit is acted upon by a force, urging it in such a direction as to make it enclose within its embrace the greatest possible number of lines of force. And that's the, I showed you guys that I think last week, but if you put the nail close to the solenoid, then it'll actually suck the nail up inside the solenoid, which is the principle of the actuators and automation. And that's Maxwell's rule. He's saying that it seems that what's happening is it's wanting to enclose that into the greatest possible number of lines of force inside of it. Really, the best way to think about it, though, I think, is to say that this coil of wire is inducing a magnetic field into the nail, which then they're attracted to each other, and then that attraction is what sucks it inside of it. It says the current loop tends to first attract and then suck the magnetic material inside the current loop. And then a solenoid, of course, is just a wire wrapped around, for example, a straw that I have here. They're important because they create controlled magnetic fields that can be used as electromagnets. And this kind of shows the analogy between a magnet and a solenoid. It shows that they can be made, if you properly construct them, to look virtually identical to a magnet. And if you think about this, current flowing through this coil, what is it? It's electrons flowing through a wire, right? Well, we also know that atoms have electrons around the atoms and that they spin, right? So one thing you could think of is if you have a piece of metal and you have all the atoms for some reason have all their atoms oriented in the same direction, it would be equivalent to having almost like a current flowing through that, right? Normally, most material has their atoms are randomly oriented, so you have no net effect. And that in reality is exactly what happens. Okay. This is showing you an iron core solenoid versus an iron core solenoid. The B field of the iron core is going to be stronger, or in other words, this magnetic field is going to be stronger, which is represented by more lines of force. See how this one has what? 1, 2, 3, 4, 5, 6. This one has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this one will be stronger because of the permeability of this is greater. Okay, so here's just another diagram of what's going on. Electromagnet section 328. It says the strength of the electromagnet is proportional to the strength of the magnetizing current, to the quantity of electricity that circulates around it. Now this is only true when the iron core is far from being saturated. One thing I did not mention is that let's say that you make a solenoid that's using an iron core, for example. Well, what happens when all the magnetic domains inside that iron core are aligned? It no longer enhances the magnetic field of that material. So it no longer makes that magnetic field strength greater. It would be as if now you have an air core solenoid. So this piece of iron in my hand, once I fully magnetize that, it's what we call saturated. All the magnetic domains inside of this piece of metal are now aligned. Okay? And now it's going to behave, the inductance of that solenoid is going to drop off greatly. Now in a power supply or something like that, that could be catastrophic. That means that your 20 microhenry or millihenry inductor is now a 1 microhenry inductor. So it's not going to operate properly. So in electronic equipment, you have to design your inductor, which this shows a power inductor here. And you have basically have a iron powder ceramic type ferrite bead thing, we call it, but a piece of ferrite. It's powdered iron and ceramic, and it's less magnetic than iron, but the whole goal of that is to prevent that core from saturating. So you have to choose one big enough to where it will not saturate. This says the strength of the electromagnet is independent of the thickness and the material of the conducting wire. The strength of the electromagnet is independent of the diameter of the coils. Another important thing about the laws of electromagnets is a current requires time to magnetize an iron core to the full extent of its power. So there is a time delay, and that time delay is what gives inductors their properties of creating a time delay. It helps them create, for example, filters. And I don't know if you guys have ever seen these little circular things wrapped around your cables, like your USB cables. Have you guys ever noticed those? That's what that is ferrite. That's what it is, ferrite. And what it does is it enhances the permeability around that wire so that it will slow down the current, so that it basically acts like a filter. It prevents this wire from becoming an antenna, is really what it does. And that's why you notice that it's really close to your computer, because it'll filter out the high frequency noise, or the noise that is going to want to tend to radiate out in space and violate the FCC rules. And sometimes equipment, you'll come with a attachable ferrite, and that's a countermeasure because they failed their FCC requirement on not radiating energy at a certain distance, so sometimes they have to retrofit the component.
Oh.
Sometimes I don't know if you've seen that before. You'll see like a snap-on ferrite.
Right.
That's because they failed the FCC's requirements, and they had to throw it in the box, and probably 90% of people aren't going to use it, so it's still going to violate the rules. So that's one of the reasons we have so much noise. But yeah, current requires time to magnetize an iron core to the full extent. Partially due to the current does not suddenly attain its full strength, but mostly due to the solid iron itself taking time to magnetize. Okay, it takes time to reorient those domains. It doesn't happen instantaneously, right? So there's a time delay. Got some nice videos you guys can watch. I'm going to go grab one more demonstration because we have time, right? Hopefully. Let's check. Let me grab a demonstration real quick and I'll show you guys a quick one.
What time does this go? 10 minutes.
Well, maybe how long? I used to have a lenses law apparatus that I had. Maybe it's over here somewhere. Oh, here it is. I got it. Got it right here. Okay. So we talked about Faraday's law. If you guys want to come up here and see this illustration. One of these is a magnet, and the other one is just a piece of steel. Okay. For example, this one is a magnet. Okay. And this one is just a piece of steel. So if I take this and drop it inside, this is just a piece of copper. There's a hole in it, so you can just put on. You see what happened there? It just fell, right? Gravity. Higgs boson at work, right? Now this is a magnet, so what's going to happen? Let's see what happens. Okay. Is it going to behave any differently?
All fall slower than. Goodness gracious. I thought we'd be letting us do.
Yeah.
He can't see over there.
This is actually how a lot of roller coasters slow down the ride. By that same principle. So what do you think's happening there?
Counter EMF, overcoming gravity, reducing the gravity force of gravity.
Well, this is a you could think of this as a continuous wire, right?
Right.
Up and around. So the changing magnetic field inside of a loop, right, is going to do what? Induce a voltage, which is basically the same as saying create a current. Inducing the voltage is saying, what is a voltage? It's an EMF. What's an EMF? It's something which tends to move electrons. What is moving electrons? It's current. So basically, it's causing a current to go around there, and that current is what? It's constantly changing, because gravity is moving it, so it's constantly changing. So it's a constantly changing magnetic field, which is what? Going to induce a magnetic field. It's going to tend to oppose what's causing it. Okay, that's pretty cool, right? You guys want to play with it? Here. You guys can pass it around and play with it if you want. You guys can sit down. You can pass it around and play with it if you want. So we demonstrated electromagnetic induction. We demonstrated Lenz's law. That's Lenz's law. What Lenz's law says is it gives you the plus or minus sign in Faraday's equation, which says Lenz's law that the direction, we're talking about direction here. That's what Lenz's law does. Faraday's law says that it happens. Lenz's law gives you the direction. It says that the induced magnetic field is going to be in the direction that tends to oppose what caused it. Okay? Which is similar to saying for every action there's an opposite and equal reaction. If I hit this, it's going to tend to oppose me hitting it, right? So it's the same sort of principle.
To oppose what?
The direction of the induced magnetic field is going to tend to oppose what has created in the first place. So the equal and opposites are going to cancel. Okay. So for example, this projector sitting over here, or this meter here sitting here, is causing a force on this table, and this table is pushing back up on it. So those forces are canceling each other out. That's basic statics, if you've ever had a statics class. So we demonstrated this solenoid generator with the guitar amp, and we demonstrated the paperclip guitar pickup. There's some videos you guys can watch. How to make a speaker. I actually thought this was kind of cool. Not able to. Oh, not. I thought this was really cool. Most of these videos I put up here a long time ago, and I don't know if all the links are still good. We can check one out here in a minute. There's a lot of cool things you can do with magnetism.
It's the
drawing magnet. Solder. For now, we're put that aside.
I'm just going to fast forward it.
It's
He's making basically an electromagnet.
after a while you're gonna have I took the 2 wires from the coil.
Wait, I'll let you see this step.
Now we're gonna take the 2 folded pieces of cardboard and tape them onto the paper plate. Now we're going to tape this onto the CD cover so that the magnet is inside of the coil. Make sure the coil has enough space to move up and down freely. You don't have to, but I usually tape the wires onto the CD cover. Alright, now we're good to go.
Not the best quality, but if you're on a deserted island and you want music, all you need is copper, zinc, and salt water to charge your battery. Do what? You have to charge your cell phone with a homemade battery and make your own speaker.
You say most cell phones will work on 8 volts?
Most microprocessors are. The cell phone adapter. The cell phone adapters are 5 volts, but then inside of it they regulate those down to probably 1.8. Anyway, I mean, there's a lot of cool videos. You guys can watch these. So in 1931, Faraday discovered that the currents can be induced in a. Okay, so first thing he discovered in 1821 was magnetic rotations. 10 years later. He started doing all the work on electrolysis, and he discovered like fuel cell technology. He discovered that in the 1820s, which I would really have loved to show you guys a fuel cell thing, but I didn't have time to set that up. That was a couple of days ago when we talked about batteries, but I'll try to get that thing working and show you guys eventually when I get some time to work on it. So he discovered that the currents can be induced in a closed circuit by moving magnets near it. Also, the circuit may be moved and the magnet fixed. And the phenomenon has been termed electromagnetic induction. If a coil of wire be connected in a circuit with a galvanometer and a magnet be inserted rapidly into the hollow of the coil, a momentary current will flow around the circuit. Okay, we already demonstrated that today. So he's just taking this magnet and moving it inside of a coil, and he's producing a voltage, which is Faraday's law. The more it says the induced current caused by withdrawing the magnet is in a direction that would tend to magnetize the magnet with the same polarity direct current. The more rapid the motion, the stronger the induced currents. So this is where he got the idea that the changing magnetic field. This is how you would say it in official. Changing magnetic field induces a voltage, But really, what he was noticing is, the faster you move this magnet out, the more the voltage. The more my galvanometer deflects. So what he would do is he would actually take his wire, this coil, and then he would put a galvanometer, which really is just another wire and coil, and see the deflection of that magnetic field. Let's see. Then this is the basic principles of. Then he thought, well, let's see. If I know that, what if I replace the magnet with a electromagnet? Replace the magnet that I'm moving inside with an electromagnet, then I should be able to get the same effect, right? So in fact, he did find that he could get the same effect by actually moving an electromagnet inside another coil. He could get a voltage over here with this instrument. Now take it to the next level. What do you think you could do next? What could you do so you wouldn't have to actually physically move anything to get an effect over here? How could you not move the coils? How could you produce the same effect over here? Change the voltage. What if you took this coil and you put it inside of this coil, and instead of you physically moving the magnetic field, what if you open and close this circuit over here? That would cause the magnetic field to appear and then disappear, right? Agreed? Which should produce the effect over here. So that's the basic principles behind a transformer. The transformer, basically, you have two coils completely electrically isolated. Okay? Electrically isolated, but magnetically coupled. You see the power in that? Because you can completely be isolated electrically from one circuit and be magnetically coupled. Okay? So which means you could change ground reference points. You could have a ground over here on this vehicle, and on this vehicle over here you can have a completely different ground reference. Pretty powerful. And you can also, by the number of windings in one, you can either step up or down the voltage by how many windings you have in one relative to the other. So that's another powerful property of that. On approaching a momentary inverse, current is produced. On removing it, momentary direct current, one which runs the same way around the outer secondary coil. So basically, one way to think of it is when you remove the magnet, it produces a positive voltage when you remove it. That's why you get the minus sign in Faraday's law. Breaking the battery circuit while the primary coil lies still within the secondary coil produces the same effect as if the primary coil were suddenly removed. Makes sense, right? At an infinite distance. So if you just take it and go, really fast, which would be hard to do, it'd be a lot easier just to break the circuit over here on this side. Making the battery circuit while the primary coil lies within the secondary produces the same effect as plunging it suddenly into the coil. Makes sense, right? So long as a steady current traverses the primary circuit, there are no induced currents. A steady DC voltage on this primary coil will induce no voltage in the secondary coil and produce no deflection over here on the instrument, unless there is relative motion between the two circuits. And really, if you think about it, this is also principle behind the speaker that you just looked at, except you had a permanent magnet here, and you had them on a spring relative to each other, and what was causing the movement was sound. By definition is sound pressure variations. Okay, sound pressure variation. So when the sound pressure varies, it causes that paper plate grabs that because it's coupled to the air. You're trying to create a large surface area with a paper plate. You're trying to couple that to your surrounding atmospheric pressure. So when the atmospheric pressure changes, it should move. So Moving the circuit, secondary circuit towards the primary has just the same effect, vice versa. By means of momentary inverse currents are induced in the secondary magnet while approaching, and momentary direct currents are induced in the secondary while receding. So there's an opposite effect there, and which is where we get the minus sign. And the current while approaching or beginning or increasing its strength, and while receding or ending or decreasing in strength. So this is a secondary versus the primary side. So with these experiments, they formulated some fundamental laws of induction, magnetic induction, not electrostatic induction. When we reflect that every circuit traversed by a current has a field of magnetic force of its own, in which these are lines of force, and that a coil of many turns has a field in which the lines of force are distributed almost identically as those of a magnet, we see that the facts tabulated below will be summed up as fundamental laws. Number one, a decrease in the number of lines of force which pass through a circuit produces a current around the circuit in the positive direction. Produces a direct current, while an increase in the number of lines of force passed through produces a negative direction around the circuit. Number two, the total induced electromagnetic force acting around a circuit is equal to the rate decrease in the number of lines of force which pass through the circuit. Okay? So that's denoted right here. If you look at E as being electromotive force, then you say that the number of lines of force, let's say you have a certain lines of force through this magnet, through this solenoid, I have a magnet here, then at time 1, and then if I move the magnet so as to create less lines of force at time 2, and this is the time delta between them, or the difference in time, then it's going to produce EMF that's proportional to the change in those lines of force. So it's just a subtraction and then division. And of course you can use Ohm's law to say what the current would be. The current, we use I today, we don't use C anymore. The I would be equal to electromotive force divided by R. But we already said electromotive force equals N1 minus N2 over T. So if you substitute there, then it would say if N is greater than N1 and there is an increase in the number of lines of force, then N1 minus N2 will be negative quantity. And this will be your equation. So you have the resistance over the change in the flux, and you also have it's inversely proportional to the time. So the quicker it happens, the more current you will produce. Which was alluding to what I was saying before when I mentioned that in the Lenz's law apparatus, to say that you induce an EMF by changing the magnetic field also implies that you also produce a current. And that's what this equation is showing you. That the only difference is you have to divide by R. Over here you have electromotive force, you're just dividing by T. But with this equation to calculate the current, you also have to divide by R to get the current. Another way one way they decided that they could measure this voltage, and the way that another way they decided that it was having to do with how many lines of force went through the coil, is they would just simply move a wire back and forth across a magnet with a magnet fixed, and this wire still as well. They would just change the loop of the circuit and see how much voltage they could produce. And I'm not really going to go into that well, because it's a little bit too much information, I think. But so that's Faraday's law. This is the way Faraday's law looks as a modern equation. Now the equation I showed you before was it where we had N1 minus N2 is an algebraic way of representing this, but this is the differential calculus way of representing it, which I know you guys probably haven't had calculus, but this you may see this equation, so I think you should be able to recognize what it is. It says the electromotive force produced in a coil of wire is equal to the number of coils in and times the time rate of change of the magnetic flux. Okay, d phi means a change in phi, and the phi you have to know is magnetic flux. So these symbols, okay, this magnetic flux is represented by this symbol. The number of turns is represented by this symbol. And the fact that it's a function of time is represented by that symbol. This symbol represents EMF. And the minus represents what? Remember the Lenz's law apparatus that I passed around? It tends to oppose. That's why I get the minus. If it was plus, then it would tend to build up and it make the magnet fall even faster. But it's in a direction that tends to oppose what started, so that's why we get a minus. Something that's minus, I mean, if you're going this direction, someone else is going this direction, you're going opposite directions. You're going to oppose each other. So that's how we represent opposite in math, is with a minus sign. Opposite directions. And Lenz's law, Article 396, in Article 320, it was laid down that a circuit traversed by a current experiences a force tending to move it so as to include the greatest possible number of lines of force. But if the number of lines of force be increased, during the increase there will be an opposing or negative electromotive force set up, which will tend to stop the original current, and therefore tend to stop the motion. That's exactly what we just demonstrated with the Lenz's law apparatus. If there be no current to begin with, the motion will generate one, which being in a negative direction will tend to diminish the number of lines of force passing through the circuit and stop the motion. Lenz in 1834 summed up the matter by saying that in all cases of electromagnetic induction, the induced currents have such... See, now he's talking about induced currents. Sometimes people talk about induced voltage, but really they're analogous. If you know Ohm's law, you know that the relationship between a current and a voltage is simply what? V over R. So it's going to be proportional. So the induced currents have a direction that their reaction tends to stop the motion which produces them. This says is a common way. Lenz's law is a common way to understand how electromagnetic circuits must obey Newton's third law, the law of conservation of energy. Energy can neither be created nor destroyed. Lenz's law is named after Heinrich Lenz. Okay. Lenz's law is shown with a minus sign in Faraday's law of induction. Let's see here. How much more do I have? Okay, I have quite a bit more to go. I think I want to show this, though. Just look at this for a minute. Now we have a course called Electric Machines. And in electric machines, if you guys are in the program, you're going to learn a whole lot more about motors and controls and all that. But for you who are getting just certificates or whatever,
two of the most important applications of the relationship between electricity and magnetism are the electric motor and the electric generator.
it's not really very easy to skip forward in a YouTube video sometimes.
The electric motor.
Yeah. What's going on?
Two of the most important applications.
Okay, well, we'll just forget about it. Oh yeah, we're just going to forget about it. It's not going to work. Sorry about that. Maybe this one will be better.
Welcome to Behavior Tech Labs.
This is kind of the inside of how
no plastic shielding outside. Instead, it has
this is how a motor is built. It's kind of neat. Some CAD drawings. And you can see that the coils of wire wrapped around. Basically, you make an electromagnet. And you put this is a magnet, permanent magnet, north and south poles on both sides. And then you got the commutator right here. This is the carbon with this actually causes the field to flip, because if you didn't, then you would just have something, it would just be an attraction and it would just vibrate and then it would stop. But if you reverse that direction of this electromagnet every time, then it's always going to try to attract this north, because you're creating a south pole that's attracting a north pole, and it's constantly reversing that motion. So go ahead and read the article. Let me see if I can find So the assignment is to read 391 through 411.
391 through 411.
So I got a red pen. Make it all the same. 391 through 411. And that's just going to finish up the magnetic portion, and then we'll be done with that book. And please make sure you take notes, because I notice a lot of people are not getting their points for the homework grade for the class. And remember, that's like 100. That's like 200 points.
Right.
So all you got to do is take down a few notes, and you'll get 2 points a day.
Wednesday, Thursday, Friday last week.
I don't really know exactly what days they were, but this is the reading assignment. So these are the numbers. These are not the page number. These are the section numbers, like these numbers, the paragraph numbers. Those are not page numbers.
Yeah, I've got them wrote all of them down since class started.
You can find it on the Moodle if you go to Moodle. It's on there.
Yeah. So, for example, 391. You make sure that whatever you're reading is what we talked about, because if you read something obscure, then it's not the right thing. Let's see here. See right there, 391, and the 1831 microfarad discovered. Okay, so it should make sense when you're reading it.
Is this mainly says north-south on here? North-south?
What's that?
North-south or south-north? I mean,
Actually,
across the end.
I think it's actually this way. We can tell right here.
Oh no, I can't get to it.
See there? This is the north side. See, this is the south side.
Okay, so there's nothing in.
No, it's right here.
Maybe we can get to it over here.
So you had to make this was north-south rather than raking. Let's see. Rather than raking it along this way, you would rake it in order to get the most density of the flux lines.
Mm-hmm.
Right? You go across the end of this is across the end of it. Basically, is right. Which way that runs to is across the end of it too.
Yeah. Yeah.
Yep. Is there any way that I can unhook your amp, or are you going to be needing it for the next class also?
What do you mean?
From your
Yeah.
power bar.
You need the power right there?
Yeah, all right, maybe I can go down to your next power bar.
No, you can use it.
You sure?
Yeah.
I don't want to. I'll plug it back up if you want.
No, I don't need it anymore. I'm good.
Okay.
I'm taking it home.
Okay, thank you. This one, right?
Mm-hmm.
I appreciate it.
Yeah.
We'll let it pass this time.
Where is the circuit in this apparatus?
That's just right
You
there.
can't have a current that's goes just around the.
Yeah.
Is it slower through the solid portion of it than it is through the rest of it?
What's that?
Does it pass slower through the solid portion of the pipe than it does through the
I don't
cutout
know.
section of the pipe?
But eddy current, you've heard of eddy currents before? Yeah, eddy currents occur in the metal itself in transformers. That's why they have the lamination. Laminate. It prevents the loop.
So
So
if you take the grounds, if you got 3 grounds, make it the same circuit, make the ground, and you make one of them longer than the other, it'll hum like crazy.
Mr. Halstead, I was going to ask you if there's something.
yeah, we just.
Okay.
Actually, you can tell a little bit of a difference.
Yeah, it does, don't it? It'll
When
slightly
it hits
slower
this
when
hole
it's
here, if you go like this. Wow, you can see it there. Let me just put it down.
Yeah, it's a lot slower through the solid pipe.
It's slower. Well, maybe. It seemed like I saw a while ago. Maybe hard to see.
I thought that. Down.
It seemed like it sped up a little bit.
Yeah. This is just a short.
A little bit. Yeah, so we would say you could call it eddy currents.
We call it counter EMF, right? What we used to call counter EMF. Y'all call it
Yeah, I like that too. It's pretty cool. It's pretty neat. What was your question?
A material being magnetized, can it only be magnetized up to a certain extent, and then where it becomes saturated, like you said? All right, so there's a certain point that any given material, like a certain material, can only be magnetized to a certain point. That's it.
Mm-hmm.
And so, is there a value of magnetism per each material, so to speak?
that's it.
Well, it's going to depends on how big it is.
Okay.
Yeah, the size of it.
So that depends on the size of the matter.
Yeah.
The density.
You're forcing the atoms to be realigned, and that takes energy.
Yes, sir.
It takes the energy away from the power of the magnet.
Okay.
So the bigger the piece, the more harder it is going to be to saturate.
Okay. Another question. Whenever we would go to do like storm trouble or power outages or something or another, I understood. Okay, like a transformer works. Like when it's out on the line, we consider it 240. It's not 220 until it goes through your meter box and your breaker boxes, and your voltage tends to die down a little as it gets to your actual where it comes out 110.
Okay.
So it's 240 out on the line. But it's 7,200 volts before it goes into your transformer.
Okay.
Then that drops down to two 120 legs, which is 240.
Mhm.
All right. After it comes out and it goes into your after it leaves your transformer and goes into your residence,
Mm-hmm.
a lot of people during power outages, of course, would use generators, and they would use it through their meter boxes. And a lot of times what we'd have to watch out for is that what they would do is leave their main on, and it would backfeed to the transformer.
Mm-hmm.
And I understood to watch out for it because it would backfeed into the transformer as 220, but it would come out 7,200. And I didn't understand how transformers would do that. I just didn't understand. I understood.
Well, it has more coils on one than it does on the other, so those are stepped down. It steps down from the main to the residential
Right.
by having a different number of coils on the primary than the secondary.
Right. But what I'm not understanding, Mr. Halstead, is it going in reverse, 220, going into in the bottom end of the transformer coming out the top, will go from 220 to 7,200.
Mhm.
It
It's
works
called a step up transformer, but basically the current at the higher voltage, the current is less.
Okay, so the same transformer will work either way,
Yeah. It's a step up transformer rather than a step down transformer.
even though it's the same transformer.
Yeah.
I understand. I just don't understand how it works.
Well, it works off electromagnetic induction.
I understand.
What it does is wherever your source is from, the
Right.
generator source,
Right.
then it produces a changing magnetic field
Yes,
in
sir.
the wire, because it's a bunch of coils of wire basically.
Right.
And that changing magnetic field is placed in close proximity to another coil of wire.
Yes, sir.
And it picks up that magnetic field, okay, and it's a changing field, and so it induces a voltage into the secondary winding, just
Okay.
like we showed today, just like the
Right.
experiment.
This
Right.
would be, if this was a step-up transformer.
Yes, sir.
This large coil of wire
Right.
would be your high voltage.
Yes, sir.
The small coil of wire. This one's going to have less lines of flux
Yes,
because it's
sir.
smaller wire.
Right.
That's your step-up transformer
Right.
if you're going from here to here, basically.
It just kind of, whenever I was first introduced to this, it kind of amazed me how 220 volts could jump up to 7,200. I mean, jumping down, I understood, but like you say, now that you've explained it, it works the same way, but backwards.
But you're not increasing the amount of power, total power. All you're doing is increasing the voltage itself. The current drops on the high when you're going. I mean, the amount of current flow is less at the higher voltage.
Right. Okay.
Yeah, the total power drops just a little bit to take into account losses
Okay.
in the.
No,
In the
you get power,
transformer.
you got voltage times amperage, that gives you power.
Yes, sir. All right, and for further reference, Mr. Halstead, questions like these, is it best if they cross my mind to write them down and wait for after class to ask you them, instead of stopping your class and asking them? You in class?
It depends. It depends on the question.
Okay, all right. 'Cause I
If
know
it's going to
sometimes-
be a long question that you think is going to need a lot of explaining, I'd wait till the end. If it's
Okay,
just a quick little question that you just didn't understand something, and,
yes, sir.
What book we need for last class?
you know, what?
What book we need for the last class? The fabrication.
Don't really need any books today. It's
Okay. I'll just leave the books.
I need to get, we're actually going, our next class, Mr. Halstead, we're going to be working on that virtual board we're building, right?
Yep.
And I'm stuck on this one part, and I cannot. This is where I about screwed up all my homework by using all my time on this because I'm stuck. And I've actually got one part of it. It said that I severed something or another, so I backed out of that. And
On the board?
yes, sir.
I don't think you're at the board yet as far as lessons are concerned.
It gets into the
last
board.
part is
The last part is
I know
the
that,
layout.
but we're not there though, are we? I mean,
Yeah,
we're
we're on
working to
6.
6 at this time.
6 at the end
is the
of
board.
6 goes to the board.
Yeah, 6 is the end of the circuitry, right? Then you go to 7 is the board.
6 is the board.
Six
Oh, is it?
board. Yes, sir.
It goes into the board. It transitions in
Yeah.
6.
I screwed up on the board too. I hadn't been able to figure out how to back it out. They won't remove the lens that I got in there. They ain't supposed to be there.
Okay, 50C. There's no problem. It needs to restart. Okay. What's the best thing? I'm new to these computers, Mr. Hofstad. What's the best thing to write these screens off with? To clean the screen. I got a touch screen computer. I didn't know what's the best thing to clean the screens without.
White vinegar.
And what kind of material? Towel.
You got your microcloth?
No,
towel?
sir. That's the best thing to use.
Something solid.
Okay.
That doesn't leave a lint. But you're using the white vinegar, keeps it from getting static.